Have you ever unplugged a running vacuum cleaner and noticed a sudden, tiny flash of light right at the outlet? That little spark happens because electricity acts a lot like water flowing in a pipe. When you suddenly yank the cord, the electricity has momentum. It wants to keep flowing so badly that it literally jumps across the empty air to reach the plug. In your house, that spark is mostly harmless, but imagine multiplying that exact reaction by 1,000,000 volts. Out on the power grid, nature and accidents test the system constantly. A falling tree can cause a short circuit, or a lightning strike can dump a massive surge of energy straight into a transmission tower. If grid engineers stopped that huge surge of power by simply flipping a giant wall switch, the resulting spark would be catastrophic. The electrical momentum is so high that the arc would become a bomb, destroying the very equipment it was meant to turn off. The power grid is filled with heavy, expensive machinery, like these massive outdoor transformers that require constant protection from those violent surges. To keep that machinery safe, the grid relies on a two-part defense system. First, there are the brains, a network of analytical devices called relays. Then there is the brawn, heavy-duty physical switches called circuit breakers. To safely stop an unstoppable electrical surge, the grid has to use the brain's logic to perfectly time the brawn's physical attack. The brains of the system, the relays, never actually touch the high-voltage electricity themselves. They sit safely inside control rooms. Think of them as security guards constantly watching the math of the power grid to spot trouble. Let's look at this animated diagram of a power generator. One way relays watch the math is through percentage differential protection. The logic follows strict conservation. If 100 amps of current flow into the machine, exactly 100 amps must flow out. If the insulation inside the generator breaks and electricity starts leaking into the metal frame, only 90 amps might exit. The relay sees that 10 amps are missing. The math no longer balances, so the relay immediately fires a trip signal to shut the system down. Protecting generators is straightforward, but protecting miles and miles of outdoor power lines requires a different logic. A relay can't measure both ends of a 50-mile line at once. Instead, it acts as a distance relay. To figure out exactly how many miles away a fault is, the relay plots electrical data on a map. This empty chart is an RX diagram. The horizontal axis measures resistance, and the vertical axis measures reactance, two ways the wires push back against electrical flow. A specific type of distance monitor, called a Mo relay, draws a circular boundary on this map.
As long as the power grid is healthy, the math plots safely outside the circle. But if a tree falls on the power line, the math changes and plots a new point. If that point lands inside that boundary, the relay knows there is a problem and triggers a trip. The relay's job is purely informational.
Once it mathematically proves a fault is happening, it passes the heavy lifting to the brawn. The moment the circuit breaker receives that trip signal, it uses extreme mechanical force to violently yank its metal contacts apart. But pulling the metal apart doesn't instantly stop the electricity. The current has so much momentum that it tears through the empty air between the separated pieces, creating a massive white-hot arc. We can see the physics of this struggle on a waveform graph. When the current finally hits zero and tries to stop, a chaotic high-frequency spike erupts across the physical gap. Engineers call this restriking voltage. The grid is full of massive wire coils that hold on to spare energy. When the main electrical flow stops, that stored energy slingshots back, oscillating rapidly to try and force the arc to strike a second time. You can see the math of that bounce in this equation. To safely extinguish the arc, engineers have to know exactly how fast that pressure will climb. By calculating the steepness of this spike, a measurement called the rate of rise of restriking voltage, they know exactly how little time they have before the spark returns. Because they know the exact speed of that spike, the breaker can fight back. Before the voltage can rebuild, the breaker fires a high-pressure blast of special insulating gas, or a vacuum, right into the gap, suffocating the arc before it destroys the hardware. Physically breaking the circuit is a calculated race against the violent physics of restriking voltage. Once that gas clears the gap and the arc is successfully extinguished, the connection is completely severed. Returning to our graph, the chaotic high-frequency spike fades away. What takes over is a normal, stable rhythm called recovery voltage. The fault is gone and the system is stable. The frontline combination we just witnessed, the fry-speed math of the relay, and the aggressive physical block by the breaker, is called primary protection.
But engineers also build a second line of defense, called backup protection. If the primary breaker physically jams and fails to open, a backup system waits with a slight time delay, ready to step in and cut the power from further away. By layering these overlapping defenses, they ensure that a single broken switch doesn't cause a cascading failure across the whole grid. The power grid functions like a giant, highly automated immune system, constantly monitoring itself for infections and instantly isolating the sick parts to protect the healthy ones. It even has specialized sensors, like the Buchholz relay, which acts like a stomachache detector. It sits directly inside oil transformers, sensing gas bubbles to warn operators if internal components are failing. So the next time you're home during a heavy storm and your lights flicker, but immediately stay on, you'll know exactly what happened. Somewhere in the distance, a relay did the math, a breaker fought the physics of the spark, and the grid safely protected itself, all in a fraction of a second.